All right, it is our start time for today's webinar. Thank you for joining us for our next installment of the IBM Quantum Industry Webinar Series. We've been doing these for a little bit over a year now, I think, and have been focusing on quantum computing applications across industries. And today we have a special cross-industry webinar to explore one particular technique and its potential use across industry domains. So today, our topic will be toward quantum advantage, algorithms and use cases for quantum-centric supercomputing. And we're excited at IBM Quantum to share with you the work we've been doing with our clients and partners in this area and the potential it holds for the future as well. So today we're joined by Dr. Charles Chung, our global lead for engineering and manufacturing at IBM Quantum, Dr. Gabrielle Compostela, our global lead for automotive and quantum, Dr. Gopal Keramor, our global lead for healthcare and life sciences in quantum, and Dr. Bob Parney, our global lead for energy, chemistry, and sustainability in quantum computing. So these are our applications experts across these industry domains, and they'll be taking us through the sample-based quantum diagonalization technique and quantum-centric supercomputing in general. So thanks for joining us today. We are recording, so we will be sharing the playback with you and those who are unable to attend live. And throughout the session today, please do post your questions in the Q&A dialog box. We'll be looking at those throughout the session today, and at the end, we'll be taking as many of them as we're able to do so. So as you think of questions, feel free to put them in that Q&A box, and we'll be looking at them toward the end of the session. And with that, I will turn it over to Dr. Charles Chung to tell us more about this technique and potential applications. Thank you, Chuck.
Thank you, Jennifer. Hi, everyone. Thanks for joining us today. We'll be talking about quantum-centric supercomputing, and in particular, one algorithm, the SQD algorithm, which stands for the sampling-based quantum diagonalization algorithm. And I think one of the reasons we wanted to do this webinar is that the potential impact of this is near-term, quite near-term. We're looking at something like a year or two in terms of being able to compute on industrially relevant use cases. And so this means we'll be able to do useful things before fault tolerance or quantum error-corrected quantum computers are available. And this brings in the impact date a lot, like I said, in approximately a year or two. So we'll talk about the quantum-centric supercomputing, the hardware, as well as the algorithms, as well as use cases and impacts. Okay. What we are talking about is combining the best of classical and quantum computing resources together. So we combine CPUs, GPUs, and QPUs together to make a greater computing whole. And this is not just simply theory. If you could go to the next slide. We are currently installing the first quantum-centric supercomputer in Japan at the Riken Supercomputing Center with their Fugaku supercomputer. Next to their classical supercomputer, we're installing an IBM Quantum System 2. It will have a 400 gigabit per second InfiniBand connection between the two machines, and its planned deployment is this quarter. In fact, I understand that the target date is next week, so it will be up and running very, very soon. Next slide. In addition to this, we have a second quantum-centric supercomputer planned for later this year. It will be running at Rensselaer Polytechnic Institute, or also known as RPI. The classical supercomputer you can see on the left is the AI MOS supercomputer, and then the quantum supercomputer will be an IBM Quantum System 1 that we'll be installing, interestingly, at a church that's about 16 kilometers or 10 miles away, and the two machines will be connected by a 10 gigabit per second Ethernet. And that will be up and running, currently scheduled to be up and running by the end of 2025. Okay, so we have two machines that are currently in the pipeline. And the question becomes, what can we do with a quantum-centric supercomputer? For example, we can simulate some industry-relevant molecules and materials before fault tolerance. And that is the important part, is that we believe that we can do this without error correction. And so if you go to the next slide, let me show you how we're doing it. The algorithm is called the sample-based quantum diagonalization, or SQD. It uses both the classical and the quantum computers together. What we're doing in this case is we're solving the Schrodinger equation. That's the equation you see here. And if you're not familiar with the Schrodinger equation, it's the quantum generalization of Newton's second law, F equals ma. So it's quite a powerful expression. If you advance one step forward, thank you. Now, the Schrodinger equation is a partial differential equation, meaning that it is a function of both space and time. We can perform a trick and separate the time component from the spatial component, and we just take the spatial component. And so that's the second expression here. You can see that the dt from the top equation is now gone, and now the expression is only dependent upon spatial variables. And this is called the time-independent Schrodinger equation. And the solution to this equation are eigenvectors and eigenvalues, which correspond to the electronic spatial distribution as well as the energy of the electron distribution in atoms and molecules and materials. And to give you an example of what we've demonstrated so far with this, on the right here, you see a molecule. This is a transition metal molecule. There are two transition metals in the molecule. Iron, you can see the two iron atoms in it. This is quite difficult to simulate classically because of its multi-reference character as well as the high entanglement in the electrons. On the bottom, you see our results. You can see three charts for eigenstate A, B, and C. The lines on the charts correspond to an eigenvector, and the y-intercept on the charts would correspond to the eigenvalues. And you can see in eigenstate C, we have found the ground state. And the y-intercept, or the eigenvalue of eigenstate C, has been confirmed for its accuracy by the state-of-the-art classical method, the DMRG method, which you see highlighted here in the dashed gray line. DMRG stands for the density matrix renormalization group. If you'd like to learn more, the paper is cited here in the bottom corner, Chemistry Beyond Exact Solutions on a Quantum-Centric Supercomputer. Okay, next slide, please. So the tidal sampling-based quantum diagonalization has two terms that are usually unfamiliar to the public. One is the diagonalization. So let me talk a little bit about what that means. So we take the time-independent Schrodinger equation, and the h psi equals e psi. And you can see that the psi's are vectors. They're just a list of numbers. The e is a single number. It's a scalar. And the h hat, the hat actually has meaning here. It signifies that the h is a matrix or a squared number. So if you could advance one step forward. Pictorially, it looks like this. So we have a matrix. You can see a whole bunch of numbers multiplied by a vector equal to a single number e multiplied, again, by the same vector. Now, if you want to solve for the eigenvectors and eigenvalues, if you could advance a step, the first step is you need to diagonalize the matrix. So it has a form that looks like, as depicted in the bottom, where there are values along the diagonal of the matrix, but everywhere else, all the values are 0. And then once you have diagonalized this matrix, you can then find the eigenvalues and the eigenvectors for this. Eigen is a German, it comes from German, it means characteristic. And the eigenvalues and so these are the characteristic values and the characteristic vectors for the time-independent Schrodinger equation. And these eigenvalues and eigenvectors are special. So if you could go to the next slide. The way they're special is the eigenvalues and the eigenvectors describe what we call the electronic structure of the atom or the molecule or the material that we're looking at. So the eigenvectors describe, as I said before, the spatial distribution of electrons, and that's the pictures you see here. Most people, if they're familiar with this, they're familiar with the atomic orbitals on the left here. This is the solutions to the time-independent Schrodinger equation for one electron. And you can see on the top, that's the lowest energy state. That's the s orbital. It has the shape of a sphere. The electrons are distributed around the nucleus in a spherical shape. The second line are the p orbitals. You can see there's more complex structure to them. They're two lobes up and down on x, y, and z axis. And then the third one is the d orbitals, and you can see that it has yet more complex structure and even higher energy. And so the eigenvalues or the energies of these start from the lowest eigenvalues with the s orbital, and then it increases in energy to the p orbitals and the d orbitals. If you look at molecular orbitals, the electronic spatial distribution changes wildly. It can change a lot depending on the particular structure or the molecule you're looking at. What I've what you see here on the right here is the molecular orbitals for benzene. Benzene is sort of one of the sort of classic examples used to describe how molecular orbitals are different from their atomic orbitals. You can see in this case, the lowest energy orbitals on the bottom here. And you can see that essentially what's happened is that the p orbitals from each of these 6 carbons, so a benzene is a ring of 6 carbons. Each of the p orbitals from each of the 6 carbons have combined to make these rings above and below the carbon ring. And then going up, you can see the next set of orbitals, which have the next highest energy and the next highest set of orbitals, and finally the top set of orbitals. And so again, this is the electronic structure of the of the benzene molecule. And what you're seeing is both the spatial distribution of the electrons as well as the corresponding energies of these states. Okay, so next slide. So this is what the electronic structure is, and what is useful about knowing the electronic structure? Well, some basic things like reaction rates. So if you look at this reaction on top here, the HO minus plus CH3Br goes to these other structures. If you just look at that reaction, there's no way to know basic things about the reaction, like will the reaction occur when you mix these two things together? If the reaction does occur, how fast will the reaction occur? If you look at a depiction that's typically used on the bottom, if you plot on the y-axis, the ground state energy of the electrons, in other words, the eigenvalues of the ground state energy of each molecular species. And on the x-axis, we have the reaction coordinate. There are only 3 coordinates. It's the reactants, the transition state, and finally the products at the end. So if you wanted to predict, for example, if you mix the reactants together, will this reaction proceed? Will there be a reaction? First thing to check is the energies of the ground state energies of the reactants and the products. If the ground state energy of the product is lower than the reactants, then yes, this reaction can occur when you mix the reactants together. If the products are higher in ground state energy than the reactants, then this reaction will actually occur in the opposite direction. The reactants will not, if you mix the reactants, they will not react. If you mix the products together, they'll actually react and then produce the reactant. So the reaction will go in the opposite direction. You also need to know the middle state, the transition state. You can see this, there's a hump here depicted. That there's typically an activation energy that's required in order for, you can mix 2 reactants and they don't really react. And so oftentimes what we do is we add energy, often in the form of heat. You're probably familiar with this cooking when you have ingredients in your pot and they're not doing anything, but if you add heat, then the ingredients start to cook. That's exactly what's going on here. They're undergoing a reaction. The heat adds the energy for a transition state. You have to also calculate the eigenvalue, the ground state energy of the transition state. Because if this hill, the delta G double dagger, is low, then the reaction can proceed at a relatively quick pace without adding too much energy. And it might even be spontaneous if the hill is very low. Or the other situation is the hill is very tall. And in that case, you have to either add a lot of energy, or which adds problems. It may be practical. You may not be able to add that much heat to the system, or you start getting side reactions that are undesirable, like, for example, the reactants will dissociate before they actually get over the activation state in the middle. And so if you know the ground state energies, the reactants, transition state, and the products, you can start answering basic questions like, will the reaction happen? And if it happens, at what rate will it happen? Will the reaction happen quickly or slowly, depending on the height of the activation barrier in the middle? Okay, so that's the part about the diagonalization. So if you can diagonalize the Hamiltonian, then you can predict things like start to predict things like reaction rates. So what's the sampling part of the sampling-based quantum diagonalization? Well, it's essentially how we do it, how we solve the Schrodinger time-independent Schrodinger equation. And the flow is we start with the molecule that we want to simulate. In this case, it's this iron sulfur cluster that I've shown here. Once you've selected your molecule, then you can select a basis set. And a basis set is just a set of eigenvalues or eigenvectors, or not eigenvalues, eigenvectors, but a set of vectors, such as the atomic orbitals. And you can also select an active space as well if you would like. And then we start using the quantum computer. We map 1 spin orbital to 1 qubit. for the molecule depicted in the upper left, this required 77 qubits, or we simulated this with 77 qubits on our quantum computer, which means the solution space at this point is quite large. I mean, each qubit that we map to can be in a mixture of 0 and 1 states, which means we have, if you just look at 0 and 1 states, we have 2 to the 77 states, which means we have a Hamiltonian matrix that's 2 to the 77 by 2 to the 77, which is approximately 10 to the 23. So this matrix is quite large. It's 10 to the 23 by 10 to the 23, and there's no way we can solve this this matrix with any kind of computer. So what we do with the quantum computer is, in the next step, we make an approximation of what the ground state wave function is for the electrons. That's this complicated circuit, quantum circuit you see depicted here. And then once the quantum computer makes that approximation, we start taking samples from the quantum computer. And what we see in the samples is not all 10 to the 23 by 10 to the 23 combinations of states are occupied by this approximated wave function. The samples tend to clump in this 10 to the 23 space. And so as we take the samples out, we then give them to a classical computer. There's an error mitigation step that occurs, but let me not distract you from the overall flow here. After error mitigation, then if you just look at the samples and you remove the states where you find that the quantum computer or this wave function does not occupy, then this large matrix of 10 to the 23 by 10 to the 23 can be much smaller. It can be compactified to a matrix that's like 10 to the 8 or 100 million by 100 million. So it's a much smaller matrix, and it's now at a size where we can give it to a classical computer. If we've selected the basis set well, we have a nearly diagonalized matrix, and then we can give it to the classical computer to finalize the diagonalization in the last step. We use the Davidson algorithm on the classical computer, and you should know that this diagonalization, it's generally useful to do diagonalization on large matrices, but in this particular case, it can be only done on a sparse matrix. The Davidson algorithm requires a matrix to be sparse. And so that's why a basis set needs to be selected well in order for this algorithm to work. Okay, so next slide. So that's the sampling part. So once we have that, then we can. So what can you do if you know the electronic structure? I said you can start to understand things like reactions. Well, what does that really mean in terms of impact? Well, the largest jumps in the product cost performance curves in most industries come from new materials. And what we'll do is we'll give a couple of examples in the rest of the talk. And so let me give you the first example. If you go to the next slide. So I cover electronics and aerospace. And so let me give you first an example from aerospace, and then I'll give you an example from electronics. So next slide. This is a paper that we published with Lockheed Martin. We applied the SQD algorithm to a funny molecule, CH2. CH2 seems very simple. It's a small molecule, but it's an odd molecule in that it's open shell. In other words, it doesn't have this nice state. Normally, carbon is surrounded by 4 hydrogens. In order to reach a stable configuration. In this case, it's only surrounded by 2, so it's incomplete. It's an example of an open shell molecule. And open shell molecules tend to be reactive. They're unstable. They're often toxic. And because they're so reactive and unstable, they have short lifetimes. So they're very hard to characterize experimentally because they only are available, or they only sit around for maybe milliseconds. And so empirical methods of understanding these open shell molecules is hard. There's for CH2 in particular, it has this funny characteristic in that in this upper right diagram, you can see that the lower energy state is a triplet and the upper energy state is a singlet. This is uncommon. Usually it's the opposite way around. The singlet is the lower energy state and the triplet is higher energy state. This is at equilibrium. But as you stretch one of the carbon-hydrogen bonds, actually the molecule undergoes a phase change. And the triplet and the singlet state switch energies, and the singlet becomes beyond a certain bond distance, the singlet becomes the ground state, and the triplet becomes the more excited state. And if you look at the results down in the bottom here, you can see the ground state energies as a function of the CH2 molecule, as a function of the one carbon hydrogen bond length. We have three methods that we depicted here in three different colors. SQD is in the dark red. Our reference is this SCI, or Selected Configuration Interaction method. And we also have the CCSD method. And we've calculated these for both the triplet and the singlet states for CH2. And what you see in the purple area is that the SQD captures this phase transition at equilibrium at the bottom part of the curve around 1.1 angstroms. You can see that the singlet state in the round circles has a lower energy than the triplet state in those sort of three-legged icon. And then as you stretch the bond length, you can see that the two lines cross, and that the singlet state it has a higher energy than the triplet state. And so the SQD is correctly capturing this phase transition. And you can see, for example, in the CCSD approach, that simulation method, or that does not capture that phase transition. And you can also see that the SCI method also captures this phase transition. You can also see you can also see in terms that, so qualitatively you can see that the SQD method is capturing this phase transition. Quantitatively, you can see that at equilibrium, again around 1.1 angstroms, the triplet and singlet states are very close to our reference state of the reference algorithm. Sorry, the SCI state, and we're within a few millihartries of the reference. Above around 2 angstroms, you can see the singlet state. The SQD singlet solutions are again very close to SCI. The triplet state is doing something funky. We know that this is incorrect. It's about tens of millihartries away from the reference here. And what's going on is we have a loss of fidelity in the error mitigation. We think we know what's going on. One way to address this will be higher accuracy, which will be larger basis sets. In other words, we need to do this with more qubits on the quantum computer. There's another funny thing, the way we mapped it to our particular quantum computer, where we think future processors will also be able to solve this. So this is one concrete example where we are looking at CH2, and CH2 is interesting because it is a product in combustion. So it's useful it happens in jet engines, but it also happens in your car, as well as energy turbines used in electrical grids. And so you could, for example, monitor how a combustion is occurring by just looking at the CH2 species, for example. Okay, so this is something that we can do now with SQD. If you go to the next slide, let me talk about something that's longer term, but I think it's important for decision makers to understand the potential impact of SQD. And let me take, for example, the hypersonic passenger air travel. Hypersonic is a descriptor for aircraft that can travel faster than Mach 5, or 5 times the speed of sound. And what that means is that a trip from, say, New York to Tokyo could take as little as 2 hours. Now, most people, when they're traveling between continents, usually plan a couple of days, maybe a week and a half for their trip, because the trip itself, air flight itself takes 12 hours, maybe 16 hours, so the better part of a day. And then once you land, you typically need a couple of days to get time adjusted to the new time zone. And in order to justify this kind of time, most people arrange multiple meetings sort of every day while they're in this other time zone. And then you have to travel back. That's another 12 to 16 hour trip. And then you have another couple of days of time zone adjustment. And so altogether, you're looking like a week and a half. But if you can travel from, say, New York to Tokyo in 2 hours, you could contemplate leaving, say, New York around lunchtime, travel 2 hours to Tokyo, attend a meeting at 9 a.m. local Tokyo time, and then get on the plane again and be back in New York in a couple of hours. So the whole trip can take less than a day. And this would transform not only the aerospace industry, but would transform the way business is conducted around the world today. Now, one of the challenges with hypersonic aircraft is that the leading edges, the nose, and the front edges of the wings can get very hot. They can 2,000 degrees Kelvin is not unusual. And what happens at those temperatures is that structural materials start to soften. They get hot, they melt, or they start to soften like butter will do when it's warm. And the chart you see on the right is yield strength on the y-axis and temperature on the x-axis. And these lines that you see here in different colors, those are different structural metals typically used in airframes. And you can most of them are nickel alloys. Inconel, for example, are the purple and green lines. And you can see that they start to bend down at around 700 degrees C, and they're losing yield strength. They're losing stiffness. However, there's an interesting class of materials called high entropy alloys, or HEAs, and you can see those in the various points at 1,000 degrees and 1,200 degrees. And you can see that these are alloys that are retaining their structural strength even at high temperatures like 1,200 degrees C. Now, one of the challenges with high entropy alloys is they're much more complex than typical alloys. As I said, most alloys used for high temperature structural applications are nickel alloys, so they have one principal component. They may have a lot of dopants, like sort of in the 1% to 2% range, but the principal element is nickel. Whereas in these high entropy alloys, you can see the formula for the highest strength alloy at 200 degrees C. That's molybdenum, niobium, tantalum, vanadium, tungsten. So there are 5 principal elements here. So just the material space of high entropy alloys is immense. If you take 80 stable elements, you pick 5. That alone is about 2 billion combinations. And that doesn't take into account, for example, differences in proportions. You could say, for example, have 2 molybdenum atoms for every one of the other atoms, for example. And so just the combinatorial space of possible high entropy alloys is immense. You're never going to be able to explore this material space empirically. That means you need to actually make the material and then characterize the material, and that will take months at least for each material. The only way to really explore this space is using computational methods. But these are materials that are difficult to model classically, and I'll tell you why in just a second. But in addition to this, even with the materials that we have found experimentally, like this molybdenum, niobium, tantalum, vanadium, tungsten, while it has remarkable properties in terms of its strength as a function of temperature, when you actually try to use it, it corrodes too easily. It oxidizes, for example, readily in the atmosphere, and therefore it's not stable in, for example, Earth's atmosphere. So again, one of the things you would like to do is, even before you go through the time of synthesizing the material and then characterizing the material, you would like to know basic questions like, is it stable? And these are questions that can be approached computationally if you know the electronic structure. So if you go to the next slide. So it takes a long time to develop new materials like high entropy alloys. The typical time is 10 to 20 plus years. I mean, 40 years, for example, is not unusual. And if you go to the next slide, one of the reasons is because if you're going to answer basic questions like, is the material stable? Is the material, for example, readily reacting with oxygen? In other words, this is, for example, delta G, or activation energy low when it's reacting with oxygen. These are questions that are hard to answer accurately with classical models, or classical approaches. If you want to just calculate the ground state energies of the reactants, the transition state, and the products, or in other words, you want to know the electronic structure of these 3 entities. Well, for larger molecules, typically you use density functional theory, or DFT. DFT is known not to be able to model reactions accurately. But even for smaller molecules where you can use wave function methods, this is hard for molecules that have multi-reference character. That includes transition metals such as high entropy alloys and excited states, such as being at high temperature. It's also true for high entanglement situations like open shell systems, but as I showed you before, we've now successfully modeled open shell systems. So if you go to the next slide.
I think, Charles, actually, let's move ahead to the other industries, if that's okay. Just being mindful of time and want to make sure there's so many great questions in the Q&A. But we'll be sharing more on this with you all soon. So we'll go ahead and move to our next industry speaker in automotive, Dr. Compostela. Thanks for joining.
Thank you, Jennifer. Thank you, Chuck. So in this part of the presentation, I'll try to give you an overview of where we see potential for the SQD method to be applied to computing challenges that are relevant for the automotive industry, and in particular for electrification. So if we look at electrification in the automotive industry, we are we can see that the industry is rapidly shifting towards electric vehicles. There's a projected market share of up to 70% EVs by 2040. And because of this, the industry is experiencing some challenges in this transformation. So first of all, there's the requirement of high capital investments with the spending on electric vehicle batteries that is expected to reach about $400 billion by 2030. We also see increasing expectations from the customers. So, for example, according to a recent survey, European customers want to have at least 500 kilometers driving range in order to even consider switching to electric vehicles. And moreover, there are also additional concerns about safety, charging time, costs that are representing additional barriers for adoption. Well, in this field, we think that quantum algorithms like SQD could offer new ways to improve the precision of simulations of key properties of materials that are used for batteries. And they could extend what can be explored entirely computationally in this area. So by doing something like this, we could help basically improve, for example, vehicle range, if we study battery compositions with higher energy densities, or we could reduce costs by discovering cheaper material candidates, or we could contribute to increasing safety of electric vehicles, for example, by exploring properties of next generation batteries like solid state batteries that are known to be safer. And IBM has already some experience in using quantum algorithms for battery chemistry. Here's an example in this slide from our collaboration with Mitsubishi Chemical. In this work, we explored the chemistry of lithium-air batteries, right? So these batteries are promising candidates for next-generation energy storage systems because they offer energy densities that are higher than lithium-ion batteries and they are comparable to gasoline. You can see this in the plot on the left. And this makes this type of battery particularly interesting for energy storage or for applications in electric mobility, as it could lead to longer driving ranges, for example, for electric vehicles. And moreover, since these batteries use oxygen from the air as their cathode material, they can be much lighter. And since they do not need any rare materials, they could also come at a lower cost than traditional batteries. So very interesting type of technology, but however, the challenge with this is that both the charge and discharge process in lithium-air batteries are very complicated and they are sensitive to the surrounding environment, so the progress of the technology has been limited by these challenges. IBM and Mitsubishi Chemical investigated the rearrangement of the lithium superoxide dimer, which requires a very accurate description of bond breaking and bond formation through a transition state that you see depicted in the right of the slide. And in this work, we used a variational quantum eigensolver to calculate the energies of the reactant, transition, and product state. And we ran this algorithm with two different iterations of the IBM quantum hardware. You can see in the plot on the right that there's quite a good agreement with between these methods, between these calculations that we performed and the exact solution using full configuration interaction that in this case can be calculated. But our expectation is that SQD could be applied to problems like this and also contribute to improving the precision of simple VQE algorithms like this one that have been used in this case. And we think there are many problems where we could apply SQD. So one of these problems where we see potential is in the study of the reactions that happen at the solid electrolyte interface of lithium-ion batteries. In lithium-ion batteries, negative electrodes are stabilized by a passivation layer that is called the solid electrolyte interface. And this interface forms spontaneously as a result of the reduction of the electrolyte and its decomposition during the initial charging cycles of the battery, and has the effect of protecting the electrolyte from further reduction. However, this interface can continue to grow with time and with charge and discharge cycles, and this can lead to capacity loss or to degradation of the performance of the battery. And the accurate modeling of all the processes that contribute to the growth of the this SAEE is essential to understand how the batteries age, and also it's essential to ensure that they are safe. But the challenge in doing this is that the interface can form through multiple different reaction pathways. You can see just one example of the many possibilities on the bottom right of the slide. And the overall effect on the battery and on the performance of the battery depends on the relative reaction rates of the different parts. So they need to be calculated as accurately as possible in order to determine macroscopic properties of the batteries. And recently, IBM applied a variant of the SQD method called EX-SQD to a similar problem, exactly to one of these reactions in lithium batteries. So in particular, our colleagues used a hybrid quantum classical method to study the oxygen reduction reaction at lithium battery electrode surfaces. This reaction has an important role in stabilizing the solid electrolyte interface. And as a consequence, it contributes, as we said, to enhancing the battery performance, the battery safety, and also its durability. On the right of the slide, you see different intermediate steps of the workflow that have been implemented in the paper, from the geometry optimization and orbital localization of the reaction that has been done using DFT methods, until the active space selection and the EXT-SQD calculation in the bottom. So I invite you to take a look at the paper that is referenced in the slide if you want to have more information. But the point I'd like to make here is that at small active spaces, this paper showed that there is an excellent agreement between this EX-SQD method and complete active space configuration interaction, which is basically a full configuration interaction calculation that only uses a chosen active space, but considering all possible electron configuration. So the quality of the results, also one of the results of this paper is that the quality of the results was only limited by the classical computational costs associated with post-processing of the samples in EXT-SQD. So there is a lot of potential to scale this method and to apply it also to other problems where there are strongly correlated electronic systems. And we think that such problems could be found also in another area where we think SQD could be valuable. And it's in the characterization of electrocatalysts for different applications. So new electrocatalysts could make future battery technologies more practical. So for example, they could reduce the shuttle effects of lithium polysulfide in lithium sulfur batteries. And so they would basically reduce, they would contribute to reducing the loss of active material and improve again cycle life and stability of this battery. In lithium air batteries, we could use advanced catalysts to manage the formation and decomposition of lithium peroxide, which would then represent, let's say, a key enabler for achieving the higher theoretical capacities of these batteries. And also better catalysts could improve the slow kinetics of the reactions in lithium CO2 batteries, which represent a promising technologies both for energy storage, for example, in the grid, but also they could also represent an effective way to reduce greenhouse gas emission through carbon capture. And on the right of the slide here, you can see some example of electrocatalyst molecules that we believe could be analyzed with SQD, and where we think this method may provide some computational benefits or increased accuracy with respect to classical methods, since all these molecules contain some transition metals that are difficult to simulate classically. So to summarize, we believe that SQD and its variants may have several applications in problems that are relevant for the automotive sector, so specifically for electric mobility, and we are already working on some of these problems. We would be, of course, happy to further explore these topics with our partners and clients. So if you're interested, just let us know. And thanks for listening. With that, I'll pass it on to my colleague, Gopal.
Life science and its potential application of SQD in healthcare and life sciences. So the agenda for the short talk is going to be what is the role of SQD in healthcare and life science. We will understand that part, why SQD for the healthcare and life science industry, such as pharmaceutical companies, CROs should be interested in such methods. And then I will show you a real world application we have a collaboration with the Riken and then the Cleveland Clinic, okay? So first thing first, pharmaceutical R&D process, we all are aware of that. It is very time-consuming, non-linear, and expensive task. And if you're interested in knowing what are the different applications of quantum computing in every functional areas of drug discovery and developments, from target discovery to virtual screening to preclinical, clinical 1, clinical 2, clinical 3, trial and post-commercialization, we have already covered this in our previous webinar, which is the application of quantum computing in healthcare and life science. But today we'll be focusing on SQD part. So if you see the SQD part, its main application is in the virtual screening, which is basically hit generation, and lead optimization. What we do here, we basically have to find a molecule. That molecule come from different molecular formats, like a small molecule. It could be oligonucleotide, it could be peptide, enzyme, antibodies. But the main challenge is that you have to find this molecule in such a way that it has a desirable pharmacokinetics and pharmacodynamics properties, right? Such as stability, synthesizability, and there are so many properties which are important. Why this property is important to predict before that molecule goes to clinical trial is because there is a 90% of attrition rate in clinical trial, right? To have a safe and efficacious drug, it is very important that we have an accurate simulation of the molecules before that molecule goes to the clinical trial, right? So that's why it is very important to have a very accurate simulations packages. So how do we do simulation today? By classical techniques. This is a plot which shows you different methods, but the x-axis is the cost of calculation, y-axis is the accuracy, and these are the different methods by which we do a lot of simulations today in today's world, right? Be it a force field simulation, semi-empirical methods, at most we can reach to the DFT level, right, which is accuracy. But what we really want, we have seen from previous speakers that we really want to understand, if you really want a more accuracy, understanding the mechanistic understanding of the molecular interaction, the reaction rate, redox reaction, it is very important to solve the Schrodinger equation if the system is a multi-referential methods, right? To do that, basically, it is a very computationally heavy task, right? As we can see here. This is a very, very expensive, as you can see, the cost of calculation is high. So right now we have classical techniques or heuristic techniques, which are basically doing a compromise on the accuracy, right? So this is a sample-based quantum diagonalization, basically counterpart this particular challenge that we have. And the application would be enormous. That could be an application within the quantum chemistry domain. That means accurate binding energy calculation, ligand design, lead optimization, and things like that. So just to give you what we have done with SQD method, with the Riken. Riken is a Japanese research organization where what we have done is we have simulated iron sulfur cluster. So this is an iron sulfur cluster, which is actually bind to the cysteine molecule, the amino acid of the protein, right? As you can see here, it's an inorganic cofactor. And this is widely abundantly available in enzymes and proteins, right? And they play an important role in a biological electron transfer, catalysis, and the regulation of gene expression. So as you can see, this has a very important strategic importance in the medicine and drug discovery, because it plays an important role in different aspects. So what we have done, basically, we have cropped this particular part and we have mapped this fermionic Hamiltonian into the qubit Hamiltonian via 36 active orbital space, as you can see here, right? So we mapped this fermionic Hamiltonian into the 72 qubits, and we have then used SQD method, right? But just to compare how this SQD method gives an advantage over all the classical and other methods, this is a chart which shows if we use a fault-tolerant computer, right, which we do not have right now, right? Even though it would take 4.5 million qubits, and that would even take 13 days to run this experiment, right? Now, coming to the reality, if we just use a pre-fault tolerant quantum computer, which we have today, we have method like variational quantum eigensolver, it would take 3 million years. That is not practical, right? So what we have demonstrated in this particular study is that the same problem can be solved in a couple of hours. That means 2 hours. And if you're interested how much time is covered by quantum and by classicals, it's around 15 minutes for quantum sampling, and the rest of the calculation on the supercomputer, Fugaku supercomputer, is on the Fugaku supercomputer, right, for the diagonalization methods. So what is the implication of this result? Implication is enormous. As you can see here, this is a plot, this is a table which shows first column drugs, therapeutic properties, therapeutic indication, and which target that contains iron sulfur cluster, right? And what is the mechanism by which that drug actually interacts. So just to give you an example, hydroxyurea, it is an anti-proliferative drug, which works on a sickle cell and different types of cancers. It basically targets the LU1 target, which has an iron supercluster, and the mediation is by ROS mediation, right? The reactive oxygen species mediation. So this is exactly kind of an example where iron supercluster and a simulation of that using SQD could be helpful, right, for different therapeutic areas such as leukemia, bacterial infections, diabetes, and cancers. We have extended, in collaboration with Cleveland Clinic, our scientists from Cleveland Clinic have extended SQD method to their particular use cases. For example, they have simulated a potential energy surface of water and methane dimer, because just to understand hydrophilic and hydrophobic interaction, non-polar interaction is very important. Also, they have simulated relative energies of a cyclohexene conformations. They have also simulated the methanol, methylamine, ethanol, and water molecule. These are all the references that we have already, is in public domain. So please have a look at it. And finally, I would just say that is SQD method can be applicable for all kind of quantum chemistry simulation, and it is not, right? It is only for those chemical system which contains a transition of a metal ion, right? And that means that the chemical system that warrants a very complex configuration interactions and entanglement of the electrons, right? So for example, this is the plot which shows these are the drugs, right? These are the different metals that is involved in this particular drug reactions, and this is an SQD advantage. For example, you know, we have a anti-cancer drug that has a platinum, like iron supercluster, copper, you know, iron, zinc, molybdenum, manganese, vanadium. These are all the high transition metal ion where the electronic configuration is enormous, right? So it is impossible using a classical tools to solve that. And this is where exactly the SQD could be helpful. So finally, I would just say that it is very promising for SQD, especially in terms of application in drug design. For example, it could help understanding the protein functions, designing the specific inhibitors, and predicting the cluster reactivity like ROS or the other medications. So with this, I would hand over to my colleague, Bob. Please go ahead.
Thank you. So we've seen some really interesting work done using SQD for molecular simulation, new materials. So how does this affect, at least potentially, the energy space, including oil and gas? Well, to understand that, we need to know a bit about what are the pressures on the energy space. So one of the first is that the energy transition is requiring new energy sources and better, more sustainable refining processes. The second is that margins continue to shrink on commodity prices, so more cost-effective production at the wellhead or in the refinery. And thirdly, sustainability initiatives are changing demand for new petrochemical products and new energy sources. So new batteries that we've seen some of the work on will play a critical role in managing a more sustainable grid. In upstream, we may start to look at, can we develop better surfactants or polymer additives, basically chemicals that can improve production. In midstream, which is pipelines, can we prevent corrosion? There's just a lot of steel essentially out on the ground, and corrosion is one of the largest costs for any industry. We also worry about things like wax, asphaltane buildup, so things that are impeding our production. In refining, can we develop new fuels? Can we develop hydrogen? As we switch to more liquid natural gas, can we improve the LNG refining process? And then in the long run, are there new plastics, new products, or new processes that can influence the petrochemical space? And how close are we with SQD and similar processes? So we've seen there has been some work done, and I wanted to tie this back to how close are we in oil and gas. So the Riken work was outstanding, a new method. We're now able to get up to over 10,000 gates, used fairly massive HPC to leverage this. So clearly the future is quantum-centric HPC, but perhaps the individual molecules weren't as relevant yet for oil and gas. However, that very much changed with the Cleveland Clinic, where the researchers modeled the methane dimmer. So the methane is the largest hydrocarbon, at least that I'm aware of to date, that has been simulated on a quantum computer. And the fact that it was a dimmer with transitions means it was an actual chemical reaction. So there were inputs, there were transition products, and final products. And then the work on surface chemistry, what was built towards batteries, becomes very critical because it shows that SQD can be looked at for surface chemistry. And so in upstream, we are concerned about the interaction between the rock face, hydrocarbons, water. And this is where our understanding of surfactants comes from, and may even lead to things like how can we do better with wax or asphaltene buildup in pipelines. So what I'm saying is we've started at some fairly small hydrocarbons. In the long run, we're going to be interested in much larger hydrocarbons, but it's all about the involved active space. So there's a potential that we could be working on larger hydrocarbons sooner rather than later. So what about the future? What are areas that we think we could have an impact sooner rather than later? So this isn't work that's been done yet, but these are some of the molecules that we think are within reach. And it's important to understand that for business, there's a lot of next steps. So even if we can simulate these molecules, how do we integrate that into a commodity generating workflow? But some example molecules, NTS for stabilizers and chelating. So it's a way of pulling heavy metals. So you could see this as wellhead treatment. This could have impact at any point in refining. Iron porphyrin complexes, they're being looked at a lot in terms of ways of converting greenhouse gases directly into fuels. And then FUMOCO has been sort of held up in quantum computing for quite a while. It's the primary cofactor in nitrogenase, which is an enzyme that catalyzes it operates in the conversion of atmospheric nitrogen into ammonia, essentially, in nature, and ammonia being the key, or N2 being a key component of fertilizer. And right now, about 2% of the world's energy is actually spent on doing the Haber-Bosch process, which is converting atmospheric nitrogen essentially to fertilizer. And in nature, it's much more efficient. So can we find a way to capture that and then move forward with developing new methods to do it? And one of the first steps is simulating FUMOCO. So these are 3 molecules that are on the horizon. This is kind of an approach where...
Oh, I think we may have lost your feed there for a minute.
We start from the algorithm we think we can...
Oh, you're back.
Sorry. It's taking a little time to forward. So going forward, can we do this from a use case we know of and then apply this? So one of the big things in oil and gas, especially in certain heavy oil products, is how do we do carbon sequestration? And you can see from some of these numbers, there is a massive need for carbon sequestration as part of an entire improvement on greenhouse gases, but it costs so much now that a lot of the sequestration pieces are being abandoned just due to cost. Well, the standard way of doing it now is to inject amines into atmospheric carbon dioxide. Despite being a well-known process in terms of how do you do it industrially, the actual pathways are poorly understood for which amines can be used to interact with CO2. And if you look along the bottom here are some estimates, And understand that we got up to 72 qubits. So these are simpler amines than we would use commercially. But we can look at potentially, if you look at this 62 qubits, 60 qubits, similarly for ammonia, we are just about at the point, just scratching the surface, that we can simulate this process. So that gives you a sense of, we are in a very exciting time where we are now almost able to simulate molecules that could transform the industry, and also our ability to apply it to sustainability. So the question becomes, for any industry, why would you get involved in quantum now? We're looking ahead at full error correction by 2029, but we are already able to simulate molecules, and we think we will demonstrate quantum advantage by 2026. So why start now? Well, there's going to be three things. We need to know what workflows need to be implemented and the use cases that matter. So simulating a molecule is not a business. How do you turn that into a business, and does it affect your business? Who will be doing this work? How are you going to fill this talent gap? And what hardware are you going to run on? One of the things that people think is, well, we'll wait behind and we'll see when our competitors develop it. But as Boston Consulting Group demonstrated, they estimated 90% of the value capture is going to be early adopters. So we recommend being one of those early adopters. So start today, establish a strategic plan, and of course, come work with us at IBM. So at IBM Quantum, we have two broad categories of offerings. In general, we can offer access to hardware at a lot of different scales, depending on your hardware needs. We can also do a very garage-based offering where we will bring our technical people and training and help build your technical team. We will build a backlog of use cases so that you can get some understanding of not just what is a quantum use case, but what is a quantum use case that will have real value for your enterprise and your industry, and when and how many steps are needed to be able to take advantage of the upcoming quantum advantage and turn it into a business advantage. So in general, we'd like to meet you where you are. If you're very experienced, we can support you with just hardware. If you need to build a team, we have industry folks that have been talking to you on this call, not just myself, but all the other industries. And we look forward to helping you out. With that, I will pass it back.
Thank you, Bob, and thanks everyone for joining to share your expertise in your areas, to hear about potential applications and current client work in sample-based quantum diagonalization. We're really excited about this avenue of exploration. I see a lot of excitement in the chat as well. I will note, I saw one question about how can I get started with this? There's a link in the console for this webinar where you can link to our documentation on the SQD add-on. So there is, an open source power tool available for those who want to get started working with this technique today. So go ahead and, click on that, explore, and there's a link to, our blog and platform. You can get started today using this technique and learning more on IBM Quantum Learning as well. There's a lot of great content out there. So let's, I know we're almost at time, but I think we can stay on a little bit longer for those who are able to take some of these great questions we have in the chat. I saw one about, is sample-based quantum diagonalization methods useful for fields other than chemistry? For example, Hamiltonian simulation has been recently applied to many kinds of classical partial differential equations. So be interested to hear your thoughts to our speakers on that.
Well, maybe I'll start. We are actively exploring other application spaces. So, for example, optimization is one particular area, and the idea of sampling is and there'll be some work coming out on that is being explored in other ways. In chemistry, we take advantage of the structure of the problem, and so it's a matter of, can we find other problems where we can leverage the structure to take advantage of this sampling approach.
I'll jump in here also. Given the success of SQD, I think the novelty of it is that we're using the quantum computer to take samples. And so we're looking at sampling-based approaches for other areas. And so there's one other algorithm that we have developed for it called the sampling-based quantum Krylov diagonalization, SKQD. And it's useful for time dynamics problems. And then, as Bob said, we're looking at sampling-based approaches for other areas. And I can tell you that there's a lot of activity looking at applying it to things like optimization and partial differential equations, but nothing, as far as I know, has been published yet.
Great. Yeah, so another question. How do you choose what algorithms to work with in a quantum-centric supercomputing environment? And how do you think about evaluating their performance in terms of benchmarking against classical HPC techniques? Do you have to create net new algorithms, or is it about, sort of translating existing algorithms into this other environment? Any thoughts on that?
I'll take this. So I guess I would say that we're not really applying old algorithms. I think what we're doing is or porting them over. We're actually developing new algorithms. As far as I know, the sampling-based technique is unique. And the reason why is because this is the first time that we have a quantum computer hooked up with a high-performance supercomputer. And so given the novel compute resources, and not only novel in terms of their capabilities, but also their restrictions, it's requiring that we develop whole new algorithms. On the classical side, we are using an old algorithm, the Davidson algorithm, but it just fits the characteristics of what we need in this particular case.
Great. Yeah, there's it made me think of this one slide, I think that Jay Gambetta presented at the American Chemical Society, where it charts, progress in chemistry algorithms over time. And you can see, a little bit of progress with VQE, advances to VQE. But then when you have SQD, it really, moves the needle, this net new, algorithm discovery on what becomes possible. So just, thought of that. And but are there other comments with the benchmarking? How do we benchmark performance of SQD, say, over the other classical methods that might be, trying to approach the same types of problems?
Right now, it's primarily on accuracy. And so we're benchmarking against other state-of-the-art classical algorithms like DMRG and CCST. So it's not really about speed right now. It's more about accuracy. I do want to address this one question from Dagnachu Biru from Quantify. Is SQD the way to get to quantum advantage in 2026? And I can tell you that our leader, Jay Gambetta, who leads IBM Quantum, he is saying that it is possible that we can demonstrate quantum advantage next year if the quantum and the HPC communities work together. And probably it will be the SQD algorithm that does that, either SQD or SKQD.
Yeah, thanks for addressing that one. I saw a question in here about specific applications for, let's see, maybe this was a good one for you, Gopal. A gene expression profile can have 50,000 gene transcripts. Can quantum computing help more effectively help disease diagnosis from gene expressions? Do we have any initial thoughts on that one?
Right. So considering the present status of hardware, so quantum computing is not for a big data problem. That's for sure. Right now, today, as we speak today, that doesn't mean that we cannot solve any problem in disease biology, systems biology. I would recommend you to go to the webinar that we have conducted, where we have given an example of how quantum could be helpful for target identification, like epistasis analysis, target identification, link predictions. These are the very small size optimization problem. which are still kind of where we are using a heuristic approaches, classical tools. So this is where the quantum application will be there, but not for the 50,000 gene transcript, analysis right now.
Thank you.
Yeah.
Oh.
And I would just add, so Chuck also mentioned about the accuracy part. So of course, the benchmark with this DMRG, CCST, these are all important, right? But we are also focusing on the time, right? Because if you really see the drug, the pain points of the pharma industry is that they have to spend a couple of weeks on the GPUs, TPUs to get back to the simulation result, right? So the task is also, of course, to go below the accuracy, right? But also to reduce the time for the simulations. That's also very promising benchmark for SQD.
Thank you. All right, let's see. Other questions here. I think there's some interest in knowing, could you remind us sort of how you take the samples of state? Maybe go back to that initial part of the discussion. Are you just taking measurements from the quantum computer? Maybe you can clarify.
Yeah, that's all we're doing. We're just taking measurements from the quantum computer. That's all. So it's as simple as that.
Mm-hmm. Mm-hmm. Are there any use cases of SQD applications to get excited states accurately to simulate absorption and emission spectra?
I think this is what this new published method tries to do. So this EX to SQD method that has been used for the solid electrolyte interface reactions in lithium batteries. That is exactly the point of these methods. So extending SQD to take into account excited states, and so being able to perform more accurate calculations of those reactions where these excited states are relevant.
Mm-hmm. Great. Thank you.
I think there is this question by Casino Player Analysis that has been asked multiple times. So maybe I can just say that the optimization algorithm, I think you should have a look at it, incentive-based optimization algorithm, where quantum could be helpful. So maybe you can have a look at it.
Okay. Yeah, definitely helpful. I see one question, Gabrielle, more on near-term opportunities in automotive industry, and I will refer you to. We did have an automotive industry webinar, I think just last month, wasn't it?
Yep.
To go over applications in the automotive industry, but maybe you'd like to say a few words here, and then you can watch the full webinar.
Oh, sure. So yeah, thanks for the question. So I think there's a lot of different types of applications where quantum computing could provide benefits to the automotive industry. We have seen a few during our webinar, so if you want to go there, take a look. But today we focused only on the challenge of electrification for the automotive industry. There are others where we see quantum computers bringing benefit, like for example, in the context of optimization of difficult manufacturing processes or routing optimization, supply chain optimization. That could be one of the possible applications, or other ways to contribute to increase manufacturing throughput or quality control, up to probably in the very long future when quantum computers will be bigger and better than what we have right now. Maybe there are potential applications also to topics really around engineering design of vehicles or autonomous driving models that need a lot of resources to be trained. There are probably potential applications for quantum computing there as well, though very long term. So I think that there are many, and we just need to find the ones that are most near term.
Thank you. All right. Well, maybe one final question here. Just a reminder to the audience members. A final note. What if people are considering getting involved with these quantum-centric supercomputing algorithms and use cases? What would be your advice for first thing they should consider? Maybe we could go around and each of the speakers give one recommendation. What's your first step here?
I would start with decide who's your point person for quantum and build from there so that everything comes to one spot, and then just build up that point forward.
Thanks, Bob.
I guess I would add identify your key use cases for quantum computing. Most people have no idea what their use cases are for quantum computing. But this is important because, one, it'll give you a sense of the potential magnitude of impact of quantum computers on your particular organization or industry. And the second is it'll also give you a sense of the time pressure. You know, if it's, for example, a materials and chemical simulation, the time pressure might be something like in a year or two.
Maybe I jump in.
Oh, yeah,
go
sure.
ahead,
Go, Paul.
Gabriela.
Go ahead. All right, so I'll take
No, I
it.
think-
So I would just suggest to also discover those use cases where classical computing is a bottleneck, and where accuracy is a bottleneck, and increased accuracy would provide additional business value.
I would agree with all my colleagues. That's articulation of the use cases. What is really a limitation, right? I mean, this is really an important thing. So first, you need to articulate whether or not that method or the problem needs an SQD. That means you need to understand. It's also very helpful for myself also to understand what is the limitation of the classical tools that exist today, right? Because unless you understand that part, you cannot appreciate what SQD can bring. So I think that would be the best way to go forward.
Great, thank you. Well, we appreciate you all spending the past hour with us. The recording will be made available in the near future. I see a few questions about slides. We won't be making those available, but the recording will be available, and we encourage you to check out those resources that are linked on your console, including, you know, an opportunity to get started on IBM Quantum Platform with 10 free minutes a month to start exploring what you can do with our utility scale 100 plus qubit systems. So thank you for joining. And when you close, we do ask that you please do fill out that survey that will pop up after the webinar closes. We appreciate your feedback and look forward to hearing more about the topics that interest you all in your quantum journey. So thank you for joining, and take care.